Okay, so before the break, I told you that in the contemporary hard disk media, we have many magnetic layers. They are separated by some thin layers, and they are made up of layers with various anisotropy field or anisotropy constant that helps in achieving the switching of different magnetization layers. Okay. So, that concept can be better understood by looking at this video, where we are talking about a domino chain reaction. Okay. Let us watch the video.
Know is that a domino can knock over another domino which is about 1.5 times larger. So what I have here is a chain of dominoes. Each one is 1.5 times larger than the previous one. And the smallest domino is about 5 millimeters high and 1 millimeter thick. And I will carefully place it. And there are 13 dominoes. And the largest domino, it weighs about 100 pounds and is more than 1 meter tall. Ready? Boom. That was 13 dominoes. If I had 29 dominoes, the last domino would be as tall as the Empire State Building.
Okay, here the first domino is falling with certain kinetic energy, right? How this kinetic energy gets amplified? Any idea? How this small tile can finally switch the large tile? Okay, anyway, the answer is here.
Here we go. What's the physics going on here? Well, every time you stand up a domino, you lift it against gravity. And that stores some gravitational potential energy in the domino. And you only have to put a little bit of push to get it to that tipping point. And then you get all that energy back again when it falls over. And that's more than enough energy to knock over the next domino, which releases even more energy. So it turns out the amplification in this series of 13 dominoes is about 2 billion. So we put in a little tiny bit of energy at the beginning, and we get 2 billion times as much out at the end. But of course, we put all that energy in by lifting these dominoes and standing them up again. So that's a kind of chain reaction. You trigger it, and more energy comes out, and more energy is released each step. Let's see it in slow-mo.
Okay, so this is just an analogy. The physics is not exactly the same. Just remember, this is only an analogy. So, in a similar fashion, in magnetic recording media, we have layers with various anisotropy constant. Let me open. Just for easy understanding, that is an analogy. Let us say you have a layer with a large anisotropy field, then say medium anisotropy field and a smaller anisotropy field, So, when you apply a magnetic field, so you are reversing the magnetization of this layer and that cascades to the next layer and so on. Okay. So, by having many layers with a different anisotropy field, and if a magnetic field is coming from this side, the magnetization reversal will cascade to the larger anisotropy layer. Okay, so, this way you can switch even materials with a large anisotropy field more than the field that can be produced by a writer. Okay, so, this is the concept of incoherent switching. So, this is one reason why we have many recording layers. Okay. So, you will notice that I mean if you look at the recording layer structure, so these recording layers will be like you have a recording layer, there is a spacer layer and so on. So, you notice that there is some spacing between these layers. Okay. So, these spacer layers control the exchange coupling between these different layers. Let us say the coupling between these layers are very strong. So, if the coupling is very strong, what will happen? Let us say these layers are tightly coupled. If you do something to the soft, what will happen? Huh?
So, it will instantly.
So, if this okay, let me answer. So, if the layers are tightly coupled, you cannot reverse anything. Okay. So, you try to, I mean you apply magnetic field, you try to reverse the magnetization of this layer, but this layer is tightly coupled to this layer. So, it will prevent this happening. So, the magnetization of this layer is going to be like this. So, if the coupling is very tight, I mean if the exchange coupling between all these layers is strong, reversal of the whole stack will not happen. Okay, if these layers are completely decoupled, okay, they are not coupled at all, then what will happen? Only top layer will reverse. Okay. So, if coupling is too weak, only soft layer will reverse. Okay. So, you saw the domino video, right? Now, you know these results. Now, you come back to the analogy. So, what is the analogy for this in the domino case, and what is the analogy for this in the domino case? So, how will you explain this using the domino example?
Coupling is too weak means distance may be large, when
Yes.
it falls it doesn't.
Yeah. So, coupling is too weak is like keeping the dominoes far away from each other. That means, when this domino falls down, it does not impact any other layers. Okay. That is the example for coupling too weak. Okay. This one too close, yeah, they are just next to each other. So, you have one domino here, another domino here, another domino here, like that. Now, if you try to push, you are trying to push this whole thing, okay. You cannot reverse. Okay. So, optimization of this exchange coupling is also important. It cannot be too weak, it cannot be too strong, then you cannot achieve the reversal. So, we have to optimize this exchange coupling. So, we have some layers to control the exchange coupling, and because of all these designs, right, we can switch the recording media. So, here I show you like 5 layers. Okay. So, 3 ferromagnetic layers, 2 spacer layers, but we can have more layers. Okay. So, depending on the number of layers you have, you can go even over 20 layers for hard disk recording technology. Okay. So, this is the reason we have so many layers for hard disk recording technology, and after doing all this research and so on, we are selling them for $7 US. Okay. So, that is the irony. Okay. So, with that we will move on to the next aspect, which is about the questions. So, you have part 1, part A, part B. Part B is set by me, part A is set by Subhankar and Atul. I don't know. So, if you have question in part A, you have to ask them. So, are there any difficult questions in part B? All have been already discussed, right? There are some new questions, no. So, can I say all of you would have scored 30 out of 30 in the second part?
I have prepared the percentage like after checking. So
Percentile?
yeah, I want to check that.
Okay.
All the students' marks based on the percentile I have like prepared.
What do you want to show the percentile?
No, if you want like for your reference to see how many are correct.
Yeah, okay. Yeah.
Like this is how it happens in our college.
Mm-hmm.
So this thing they like 1 second. Yeah. So this is the maximum marks out of 50. They have total 50%. So based on 50%, how many they have got. So based on what percentage they have achieved. So above 90%, that will be AA 10 CPA. 80 to 89 will be 9. So it will be AB.
Mm.
BB something like that.
I mean, do you have any profiling for like which are the tough question or?
Which are the tough questions?
Yeah. Do you have something like that?
We have
I think this one we don't need to show them now.
Yes, yes.
Yeah.
And that also, if you like how many?
This one we will discuss after the May comes.
Okay.
Okay. Yeah. Okay, so now let us make it free floor. Any questions on the topic that we have learnt, then we can discuss, or any concepts that were difficult. So, when I taught you it was difficult to follow, but now you want to revisit and okay. Okay, so here I have so many layers. So, the question is about why do you use lubricant. Okay, so anyway, so since the question is on lubricant, let me explain the purpose of all the layers. Okay. So, we have a substrate and we are depositing so many thin layers. Okay. So, if you deposit many layers on top of a substrate, then there are possibilities that the films do not stick onto the substrate. Sometimes your films may peel off. Okay. So, if you any of you are doing sputtering or some device fabrication, sometimes you might encounter the problem of films from peeling off. Okay. So, usually we start with the layer which improves the adhesion of all the layers onto the substrate, and in the hard disk drive technology, this is usually tantalum, titanium, or some alloys of titanium or tantalum. Okay. So, this layer is meant for improving the addition of so many layers onto the disk substrate, and this you already learned, right. I mean, you want some solid platform to hold all the layers at the top. So, that is why we have a substrate. Then soft underlayer we learned that the magnetic field produced by the head comes all the way to the soft underlayer and goes back to the head again. So, this soft underlayer provides a conducting path for magnetic flux that comes from the recording head. So, flux goes through all these recording layer, write information, then it goes back to the head. Okay. So, this is the soft underlayer, and it has an synthetic antiferromagnetic structure through some thin ruthenium layer. So, this ruthenium layer is typically 0.8 nanometer. Okay, 0.8 nanometer ruthenium we deposit to achieve the synthetic antiferromagnetic property, and the purpose is to reduce the noise that comes from soft underlayer. Then we have a few layers like nickel tungsten, ruthenium, and 2 ruthenium. So, all these ruthenium layers help to provide some crystallographic texture, so that the easy axis of the other layers on top, the cobalt layers will have easy axis, C axis in the perpendicular direction. Okay. So, these are all cobalt material, right. Cobalt has a HCP 002 direction is the C axis. So, this will be in the perpendicular direction. So, one reason of having so many layers is to achieve the C axis in the perpendicular direction. Okay. So, by tuning this one, you can maximize the number of grains which will have the C axis in the perpendicular direction. Okay. If you do not have, or if you do not optimize these layers, so you will have some grains with a C axis like this, some grains with C axis like this, and so on. Okay. So, you will have some randomness. To minimize that randomness and to make more grains to have C axis in the perpendicular direction, people optimize all these layers. Okay, then we already learned this one. So, we have many layers to improve the writing process. This one we skip. Okay, we skip this one. If anyone is interested, I can teach you. Then later we have, you see, 2 carbon layers. So, these are carbon layers. So, this layer prevent all the other layers at the bottom from getting corroded. Okay. So, the carbon layers are meant for corrosion protection. So, if any of you are working on thin films, so typically you may use some layers as a capping layer, tantalum, platinum, or some such layers you will deposit on the top to make your films from getting corroded. But in the hard disk industry, we use a carbon layer to prevent the disk from getting corroded. Okay, so why we have 2 carbon? So we have 1 carbon with this carbon is deposited with some hydrogen during the deposition. The second carbon is deposited with some nitrogen during the deposition. Okay. So all these are sputtered, all these layers until the top carbon layer all are sputtered. So when we deposit the second carbon layer, we deposit the carbon in the presence of some nitrogen gas. Okay, so why we have 2 carbon layers? Because the first carbon layer, it has a good coverage. Coverage means it will like spread over the disc uniformly, and it will have no pinholes. So it's good for the corrosion protection. Okay, the second carbon layer with nitrogen is needed for something called lubricant affinity. Okay. So we designed this layer with the idea that we are going to have some lubricant at the top. Okay. So this carbon, nitrated carbon, has some chemical property that enables the lubricant to stick to the carbon very well. Okay. Otherwise, what will happen if you have a disc? Let us say I have a disc. So there will be some regions where the lubricants will stick very well. Some regions the lubricant may not stick very well. Okay. So you want the lubricant to stick very well. Okay. So if you want the lubricants to be not in patches like this, but you want them to be uniformly spread, then we have to grow this nitrated carbon. Okay, then on top we have lubricant. Okay, so this lubricant is or some polymers like the chemical name is called Zidol. If you are interested in the chemistry, you can look for this name. You can Google and find out what Zidol is. Okay, so why we have this lubricant is because, as I mentioned, we are rotating a disc at a rotational speeds of like 5,400 or 7,200 rotation per minute, which is a high speed rotation, and we are flying the head on top of it at a spacing of 1 nanometer. So, imagine you are rotating something at very high speed and you are flying at 1 nanometer. If there is some occasional contact, then the head can crash, it can crash these films. Okay. So, to prevent the mechanical crash, things like that, we have this lubricant. Okay. So, this lubricant, this whole thing helps to minimize the problem that arise when there is a crash between the disc and head. Okay. Any other questions? Pardon? Carbon is sputtered, yes. Okay, I told you until this is sputtered. Okay. I told you that until the carbon is sputtered, lubricant is not sputtered. Okay. Lubricant is deposited in some other technique. Let me show you. So, there are two ways to deposit the lubricant. So, one way is to do dip coating. So, in the case of dip coating, you slowly dip the lubricant, the disc into the lubricant. So, all these the lubricant molecules will go and stick to the disc, then raise the disc slowly, then your disc is coated with lubricant molecules. So, this one way, this is called dip coating. So, in another coating what they do is like they dip the disc into the disc, then they will drain the liquid, the lubricant. So, the lubricant will be drained away, then your disc is coated with the molecules. So, except for the lubricant layer, all the other layers are deposited by sputtering. Okay, since you are interested in this one, you better watch this video. So, this video shows so much I mean the high tech involved in hard disk manufacturing. Okay, let us play this one.
We design them to become your closest friends. Reliable, compatible, responsive, amazingly smart. You might take them for granted, but they hold your stories and memories, your pictures and videos, your music. You trust them as business partners and rely on them to provide your entertainment, knowledge, and communication. The Seagate family of drives. We'd like to share with you how we provided more than 1 billion drives to people around the world. A glimpse of the inside story. Every Seagate drive is comprised of sophisticated components. Recording heads, recording media, electronics, and firmware, all playing a critical role in the storage of information. We have hundreds of scientists and experts in everything from chemistry, physics, and process technology to fluid mechanics and aerodynamics. These specialists design and build the world's most advanced digital storage products by combining their collective expertise. All of the information stored on a hard drive travels through the recording head. This tiny electromagnetic wonder hovers less than 100 atoms above the disk, a gap 100 times thinner than a sheet of paper, reading and writing information on a surface spinning up to 15,000 revolutions per minute. To build these advanced recording heads, silicon wafers are sectioned into increasingly microscopic pieces, attached to mechanical arms called suspension assemblies. These heads are so small that Seagate's thousands of square feet of clean rooms need to be 100 times cleaner than a hospital operating room. Seagate engineers put these recording heads through rigorous testing, screening, and precision measurement before they are positioned in a hard drive. Recording media are the spinning disks that store the information on a hard drive. These disks are manufactured starting with substrates, typically made of glass or aluminum. Then, microscopically thin layers of highly specialized magnetic films are applied, enabling the storage of all those trillions of zeros and ones that make up the digital content. The disks are also polished and lubricated before a multi-disc writer applies servo patterns onto each media surface. These servo patterns create a map that determines where all the digital data can be located. The disks are now ready to be integrated into a hard drive.
They all are robots. Nobody is using hands.
This is where Seagate engineers bring together all of the heads and disks, integrated circuits and motors, software and firmware, and other critical technologies. Assembly begins with base decks, including the motors that spin the disks. Each deck has an electronic tag, similar to a digital fingerprint. that tracks the drive from assembly to testing and also stores key information. Precise and fully automated machinery combines the sophisticated components for each drive. Parts are assembled, balanced, measured, and adjusted according to demanding tolerances. Then, in their state-of-the-art automated testing systems, Seagate can analyze more than 1.5 million drives at a time. These drives will undergo thousands of tests to make absolutely sure they meet our customers' exacting criteria. Our drives are put through procedures that push them beyond reasonable limits in all phases of a drive's development to make sure they run smoothly in all kinds of systems and demanding environments. From an acoustic vault to help us eliminate noise, to chambers that simulate altitudes up to 40,000 feet and pressures well below sea level, drives are cooked to extreme temperatures. We shake and drop them, and hit them with thousands of power on and off cycles. Seagate scientists keep dreaming up new ways to test the limits, all with the goal of making sure those drives perform as promised. Seagate is leveraging more than 30 years of leadership in hard drives to develop the next generation of storage technologies. Solid-state drives and hybrid combinations of solid-state and traditional disk storage are already being delivered to customers worldwide. And we continue to push the limits of rotating hard drives with discoveries such as heat-assisted magnetic recording. The future demands increased capacity and faster performance, and this is just the beginning of what's going on in our R&D labs to meet the world's insatiable need for digital storage. Over the next year alone, people in their computers will generate 40 exabytes of new information, the equivalent of 700 billion hours of music, or 13 trillion digital photos. That's a lot of hard drives needed. Hundreds of millions of them. Seagate meets this unprecedented demand through customer-focused innovation and operational excellence. Building 6 hard drives, hybrid drives, and solid-state drives every second. And every one of those drives journeys through more than 1,000 manufacturing steps, flawlessly calibrated to provide the most reliable and consistent supply chain for the more than 1 billion devices delivered to our customers worldwide. Seagate is building the performance, reliability, and quality you depend upon, so you can store, share, protect, and enjoy your digital life.
So you can see the complexity involved in making a hard disk drive. To give you some perspective, right? So we learnt about read sensors. So in the hard disk drive, read sensor and the writing head are in a same place, okay, next to each other. One for reading, another for writing, is called integrated head. So to make this integrated head, the number of processes required, the process steps, right? For example, you clean substrate, deposit some resist, spin coat, then expose, lithography, etching. Let us say these are some examples of process steps. The number of process steps involved in making a head is more than 400. Okay, more than 400 steps are involved in making a head, and it takes, let us say you start this whole processes on day 1. To finish all the process steps, it takes 3 months. There are so many processes. So you start making a head, then after 3 months your head will be ready. So that is the kind of complexity involved in making a head for reading, writing information in hard disk drive. And suppose you want to start a company. Let's say Ambani wants to make a hard disk drive company. Then he has to get 200 patents cleared before he can make a hard disk drive, because there are so many patents cover each aspect of hard disk drive. You make magnetic recording, we saw that there are 20 layers. So, there will be maybe 20 patents just for the hard disk alone. Then you take the head, there will be so many patents. So, like that, like there are 200 different technologies you need to make a hard disk drive. Recently one company from China, they contacted me and they said they are interested in jumping into hard disk drive. Then I told him that these are the problems. Okay. So, it is very highly complex technology. You will not realize, you may buy a hard disk drive for $100, you think it is cheap, but there are so many things, physics, material science, as you would have listened in this talk, right. So, they said, for example, you talk about head flying onto the disk. So, that is fluid dynamics. So, mechanical engineers have to simulate how the aerodynamics of a head flying over the disk will look like. Then chemists are involved in the lubricant, physicists are involved in designing the head media, so many things. Then electrical engineers are writing the coding, signal processing, mathematicians come in and things like that. So, hard disk drive is a completely interdisciplinary field. Okay. So many scientists come and work together to make the hard disk drive work. Okay. Any other questions?
One question from online. Can you please explain the synthesis of substrates in industry?
Can we revisit this one? Different one.
Can you please explain the synthesis of substrates in industry?
What of substrates?
Synthesis.
Synthesis of substrates. Okay. If we are talking about, okay, depends on the industry we are talking about. I had a lot of slides, but I deleted. So, depending on the industry, we may use different substrates. So, in the semiconductor industry, we use silicon substrates. Semiconductor industry, we have silicon substrates. So, I am not very expert in this silicon technology, but basically it is like you have a seed of silicon, then on this silicon you grow the silicon crystal layer by layer. Okay, so, finally, you will have a large piece of silicon. Okay. So, people will cut them into thin wafers, then these thin wafers will be polished to make the substrate for the semiconductor industry. So, many research labs also use silicon substrate for their making their sample. So, this is one type. So, here is like it is basically crystal growth. You grow silicon crystal, then you slice them, polish and achieve the desired dimension. Okay. So, that is the process in silicon. So, in the case of hard disk drive, we have two types of substrates, aluminum alloy or glass substrates. So, here again aluminum alloy you can make by melting. So, let us say you have a sheet of aluminum alloy, then you cut them into disc Okay, so you make disc out of this sheet of aluminum, then you polish them. Okay, so you have to polish to a roughness of around 0.15 nanometer. Okay, so yesterday when I went around the posters, so some of you had roughness of 3 nanometer, 4 nanometer, and you said that that's a very low roughness. Okay. But in the industry, if you take the semiconductor technology or hard disk drive technology, we are looking at roughness of 0.15 or below. Okay. So, again why we are looking for small roughness is because if average roughness is 0.15 nanometer, the peak, so you will have the disk, so somewhere you will have some peak, right. So, this peak will be roughly 0.5 times, 5 to 10 times. Okay. So, we want to make this as small as possible, so that your peak roughness also is not that high. So, we are talking about a head flying over 1 nanometer height. Okay. So, we have to minimize the roughness to this very low value. So, if I say my roughness is 0.3 nanometer, then my friends from Seagate or Western Digital, they will laugh at me. Okay. This is not good enough for application. So, we make the disk to have very low roughness. So, that is where a lot of polishing and things like that are done. So, similarly glass also is like that. So, you make glass into this shape, then polish. So, glass polishing is very difficult, but there are some benefits. Okay. So, when you polish glass also, even though it is difficult, you still need to achieve this kind of low roughness. Okay. So, to give you some perspective, so one famous company which makes ceramic plates, okay. So, they came to meet us that they want to enter into hard disk industry. Okay. So, they wanted to make ceramic substrates for hard disk application. Okay. So, they sell plates which people buy at home and use. Okay. So, their main business is home business. Okay. They thought if they enter into hard disk drive, so typically we make like 500 million disks every year, 500 or more million disks every year. So, this is a huge market. So, this company wanted to enter into substrate business, make substrate and make money. Okay. Then we told them the process steps involved in making a glass substrate. So, how much polishing, what is the roughness needed, all those things. Then they gave up. Okay. It is not easy. So, it is like ceramic plate, what they do, they just do some processing, they sell the plate for $15. But if they have to make ceramic substrate, they need to so much process, achieve this kind of roughness, then they will only sell for $7. Then they thought it is not a good business. Okay. So, this is the kind of complexities involved in technology. There is another online question, can we revisit to understand why a high damping constant is undesirable? What I understand is that higher damping constant will result in faster alignment of magnetization along field direction and hence better speed, which is in contrary to the discussion in the sessions. There is no contradictory. I told you that there are benefits and problems. Okay. So, with high damping constant, the benefit is high speed, which I told you already in the lecture. I told you that if you have high damping constant, you can achieve high speed. So, this is the benefit. Okay. So, what I said in the class was that if you apply certain magnetic field, then damping makes the magnetization to be aligned with the magnetic field soon, very soon. Okay. So, with very short time scales you can align the magnetization along the direction of the field. So, high damping constant means high speed. So, this is the benefit. But high damping also has a problem. So, the problem is if you look at the formula for the current density required to switch the magnetization. So, that will also be proportional to alpha, okay, proportional to damping constant. So, this alpha is now proportional constant. So, I will use word damping constant, otherwise I will write 2 alpha. Okay. So, now Jc, you will notice that the Jc is proportional to the damping constant. So, what it means, if your damping constant is high, you need more current to write information. That means, you spend more energy to switch the magnetization. So, it is good in one sense and it has a problem in another sense. Okay. So, you can look for the formula about switching current, then you will realize this. Okay. So, what you heard is right, but you heard only one aspect of damping constant. There are 2 aspects to damping constant. Okay. Any other questions? Okay, anything else? I mean, until Professor Datta comes, we can discuss. Yes. What device? MTJ device. Okay.
So if the fixed layer thickness we increase, if then our polarization efficiency will increase. So is it proportional or there is some limitations as well?
Okay. So, you are talking about STT-MRAM. Okay. There may be some gain if you increase the thickness of the reference layer, okay. But beyond certain point, what happen, there are 2 problems. Okay. Let us say you make it like only 1 nanometer, then you may not achieve sufficient spin polarization, that is a problem. But from 1 nanometer, let us say 5 nanometer or 10 nanometer, there may be some significant gain, but if you go beyond that, there may be no gain. Okay. So, if you go to very large thickness, there may be no gain. Okay. So, I do not have the ready made answer, but my thinking is 2. Okay. So, first problem may be coming from the spin diffusion length. Okay. So, only for certain spin diffusion length, that will determine what is the thickness where you will have more gain. Okay. So, that is one thing. So, it will be decided by spin diffusion length. The second problem is from the manufacturing. So, let us say you make it very thick. So, what people do, they have many layers of MRAM material, then they have to do lithography. So, we have certain resist. Then using this resist as a mask, you are etching the layers to get the MTJ, right. So, if your MTJ layers are very thick, you will have difficulty. I mean, you may have to grow like very thick resist layers, and etching will become a problem, okay, especially when you are packing MRAMs at a closer distances. How you etch so thick layer and whether you can get the desired pattern. I think all this manufacturing problem will be happening. So, these two will limit how thick you go.
So is it like if the thickness will keep increasing, the polarization efficiency will saturate, or it will decrease after some point in time?
That I have no idea. I have not read about it. So, I cannot comment on that. Yeah, you can look for the answer somewhere. Yes. Anything else?
Can you explain the GMR CPP configuration also?
GMR CPP configuration. Okay. Okay, let us say we form a few layers. Let us just take 3 layers for example. Okay. So, we have 2 ferromagnetic layers and a spacer layer, and they are in certain shape. Okay, so, when we are talking about current in plane, we are talking about current going through this way and coming out. So, when we talk about current perpendicular to the plane, we are talking about sending current through the layer. Sorry, this is I. Okay, so this is current in plane, current perpendicular to the plane. Okay, so I mentioned to you that the CPP becomes useful only when the device sizes are smaller. Okay. Okay, that is because let us say if this whole thing is very large in area, so when the device is very large, you try to measure the resistance, you will find the resistance to be very low, right. Large sheet of magnetic materials you try to measure. So, basically we use something called RA, resistance area product, to define the GMR TMR sensors. So, let us say we have some RA value, you divide by a large A, then what you will end up with some low resistance. Okay. So, this is the problem. We could not use the CPP at high density data storage where the sensors were bigger, but once you go to small size, you have a reasonably larger resistance. So, let us say this is a 10 ohm. Okay. So, if the GMR is 10%, your resistance will go from 10 ohm to 11 ohms. That is reasonable, but in this case, for example, the resistance may be like 0.1 ohm or 0.01 ohm, then the change will be like only 0.1 to 0.11 ohm, something like that. So, the difference is now 0.01 ohm, which is too small to read, whereas here 1 ohm is easy to read. Right? So, because of this reason, CPP was not useful at low densities. Early days of hard disk, we were using bigger heads, so it was not useful, but when we go to high density, we are making the heads smaller and smaller. At that point of time, this becomes useful. So, that is one thing. Second reason why CPP is useful is because in hard disk we have some shields, right. So, between on both sides of the read sensor you have some shield. Let us say here we have some shield material. Shields are basically soft magnetic materials like say nickel, iron or something like that. These are metallic. Okay, so, similarly at the bottom also you have some soft magnetic material like these, which are magnetic and metallic. So, you can send current through the shield, through the device, and it will come through the other side of the shield. And because of this reason, you are minimizing the spacing between shield and shield. Okay. Shield to shield spacing is reduced. So, this also helps to achieve high density recording. Whereas, in the case of CIP, you have some shield here, you have metallic layer here, and you do not want this current to be shunted by this metal. Okay. So, it may be shunted by this metal or the other metal. So, you have to grow some insulating layer. So, this insulating layer adds to the distance. So, the shield to shield spacing increases. So, this is a problem. So, what was your specific question here?
No, the configuration.
Configuration. Okay. Any other questions? Yes.
Can you tell about the D0 ferromagnetism?
D0 ferromagnet, I have no idea. Maybe you can teach us. Okay. I don't know. I haven't read about it. Magnetism itself, there are too many things, so wide knowledge, we only know a little bit. Okay, maybe something off topic, non-physics. So, when I was, you remember that day I duplicated a slide and I was trying to make a figure bigger than what was in the slide. Then I was spending a lot of time. Do you know why? Okay. So, what I was trying to do was to keep the aspect ratio of the image same. Okay. So, what is the aspect ratio? Let us say I have certain image. So, this image has 400 pixels in this side, 300 pixels here, and currently this picture occupies say 3 centimeter times 4 centimeter area. Okay. So, now I want this image to occupy a bigger area. Okay. So, when I do that, I should make that a multiple of this one. For example, I can make okay, what is the number I can say? Yeah, 9 by 12 or something like that. So, let us say I zoom in, then finally one side is like 9 centimeter, another side is 12 centimeter, that is correct aspect ratio. So, this ratio is still 3 times 4, right. So, this is called aspect ratio. So, whenever you deal with figures, do not change the aspect ratio. Okay. So, you have to keep the same aspect ratio. So, quite often I see, especially among the Indian students, that you do not give any respect to this aspect ratio. For example, if a person is like this, okay, so either you make him like this, like a cartoon or like this. Okay. So, either you press on one side or compress on the other side and make him a cartoon. Okay. So, this is with people, and it happens with so many things. Yesterday also I saw many posters where the poster is supposed to be of this size, but during the printing or something the poster got elongated like this in one direction. So, all the fonts were, let us say if A is supposed to be like this, A was like this. Okay. And some cases Gyan was like this. Some cases Gyan can be like this. Okay, this is not correct. So, this I see quite often in India. So, respect the aspect ratio, maintain whenever you deal with pictures, maintain the same aspect ratio. Okay. So, here is 3:4, right. So, when you make it bigger or smaller, you should maintain the same. So, in PowerPoint you can do that. I could not do it here because I was dealing with the website, but with the app you can do that. So, if your friends do, educate them, okay? Educate them to have same aspect ratio. And another point I want to suggest about the poster presentation, that when you are creating a poster, right, when you create a poster, there may be people who are near the poster, some people may look at your poster from far, all should be able to see. Okay, so if you want all of them to be able to see your poster, the minimum font size this one no need to record, all off topics. Okay, so if you want all of them to see your posters, the minimum font size, the height of the font, for example, let us say you have A, letter A, this font has to be like 1 centimeter tall. Okay, so in the case of printing technology, 72 point means 1 inch, which is 2.454 centimeter. So 1 centimeter is equal to roughly 30 point. Okay. So in PowerPoint and Word you are using points to define your font size, right. So you use at least 30 point or 32 point when you design poster. Okay. Don't have too much text, thereby making your letters too small. Okay, I saw posters with 14 point or so. Okay, this is not good. So your poster should have fonts of this size, roughly at least. Sorry?
We should stop the recording.
Yeah, they can show.
Like we have to first formally conclude like online participant, because this recording.
Oh, okay, it's okay, it's okay. Yeah, it's okay, no problem. Okay, any other questions or discussion? Okay, since we have nothing much to discuss, let me take another feedback. Okay, now we are at the end of the course, so please give the clap feedback again. Okay. So we took one during the middle stage, so let us do one more. Okay, so please join. Okay, let us start. Okay, next one. next one. Next one. Next one. Next question. Okay, next question. So, for the online audiences, you have missed the neuromorphic computing discussion. I will share you some other YouTube link which you can watch and learn about neuromorphic computing. Okay, I will wait until 25 and move to the next question. They are taking too long time. Okay, I will just wait for first 20. Okay. So once 20 people answer, I will move to the next question. Now the answers are coming rapidly. Okay, next one. 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 Okay, next question. Okay, next one. So last two questions. So this is the penultimate question.
After this, like you formally just say that that's it for today. So we'll just remove the online participants, and for offline we can proceed further.
Okay. Tanmay said there is
He said that he will be coming. He's coming.
is coming in a few minutes, so we can wait, right?
Yeah.
So you mean they can go? Will they?
Recording will be continued for till last night. So I think these online participants, you can just ask them to leave.
They can leave, right? Yeah. So all the online participants may leave now. Okay, if the online participants are listening, you may leave now. Okay, so this will be the last question. Okay, thank you. So we'll wait until Professor Tanmay Datta comes. Until then, we can discuss if there are any more questions.
I can announce that the certificate distribution will be happening.
Pardon?
I can
Yeah,
announce
yeah.
that. I can announce that.
Mm.
So we have to wait till the Tanmay comes here. So after that we'll distribute the certificates also, and then we'll have the lunch here only at the CET. So today there will be lunch at CET, okay, for all the participants. And then if you have anything to ask, like apart from this course also, you can discuss this, sir. Okay.
Okay, I can show you some more videos which I skipped during the course because of lack of time. Okay, so in hard disk industry, right, especially the disk media industry, we are making something like 900 disks per hour. Okay, so if any of you are doing sputtering or any thin film deposition, so you know how much time you take to make one sample. Okay, you may take 1 hour to make one sample, or maybe you may make 2 or 3 samples per day. Okay, but the hard disk industries operate at 900 disks per hour. Okay, so how we can make 900 disks in 1 hour is through this kind of process. For example, I told you that there may be like 24 chambers. So in a disk sputtering system, you have like many chambers, 1, 2, 3, all the way to 24 chambers. So the disk will go in and come out like this. Okay, let me play the video. So the disk goes in, deposition happens in station 1, then the disk goes in, deposition happens in disk station 2, and so on. So by that time this has reached 2, right, another substrate will enter. So all these substrates go in queue one after another. So when this disk is in N, there is another substrate here, another substrate here, and so on. Okay. So all the disks go in sequence, and if let us say in each chamber, I mean the time taken for a disk to go from one chamber to the other chamber is only 4 seconds, for example. So within 4 seconds the sputtering happens and the disk has moved from one chamber to another chamber, for example. Then we can have 900 disks per hour, because every hour has 3600 seconds, right. So this is how the hard disk industry can achieve high throughput. Throughput is basically how many disks you can make an hour. So this is the sputtering machine we had in our lab. This is a production sputtering machine, old production type of machine. So here you will notice that we have loaded the disk here. There is a disk you can see here. So that disk will spend some time here, sputtering happens, it goes to the next station, sputtering happens, it will go to the next station, sputtering happens. So here, for visual idea of what is happening, we have opened this chamber, but during the sputtering there will be a door, this side door, this will close. So that door also has another target. So in hard disk media we have 2 targets, so 2 guns. So the deposition happens from this target and this target also. So when the disk goes in between 2 targets, both sides will get sputtered. So by making this kind of process, we can achieve many disks in every hour. Any other questions?
Sir, any more suggestions to make a better poster presentations? I mean, this font size and aspect ratio.
Okay,
But,
font size, aspect ratio. I mean, usually aesthetics cannot be taught. Okay, so I don't know how to teach aesthetics, but you can all try to. So even with my students, quite often I tell them to change the colors. So my default, I mean, whenever you guys try to plot a graph, you are probably using origin, and origin throws in black, red, green. Okay, so all the graphs come in black, red, green. So my rule of thumb is never use black, green, red. Use some colors different from that. Then there are, I mean, if you want to use colors, right? There are many color templates. So, for example, so if you are publishing in some journal where you want to make your images to be, I mean, distinguishable even for people who have color blindness. So you can go and come with some template like this. You can use these colors for your graphs. And another thing is, like these days worldwide people don't use the serif fonts. For example, Times New Roman, hardly people use it. So people suggest using either Arial or Helvetica, those kind of font, for example. Arial, you know, okay. Arial is one type of sans serif font. So Helvetica font will look like this, So people are using this kind of fonts. So, but quite often I see here people always use Times New Roman. Okay, Times New Roman is so boring font. So these are sans serif fonts. You can use them. And in poster presentation, one point is that, okay, suppose the listener comes. Listener may have 2 minutes or 3 minutes, 5 minutes, or he may have interest only in certain aspect. So you should be able to tailor your presentation to suit the listener. So you cannot have like only one way of going from introduction all the way to the conclusion. You should be able to fragment and just focus on your presentation tailored to that particular customer. Okay. The color contrast also is some issue. So sometimes people will use dark color background, and the font they also use will be dark. Okay, that then people cannot see. So you have to use, if your background is dark, then the font has to be light, white, yellow, light yellow. Okay. Okay, another point maybe I can say is like when you guys read paper, right? When you do literature survey, you read papers. Usually, you read with the aim of understanding what is there in the paper. Okay, that's okay to start with. When you are a PhD student, you can do that. But at some point of time, your thinking should be not in exactly grasping what is written in the paper. Your thinking should be like halfway through. You should be think, what if you should come up with some idea. So the paper you read should trigger some idea that should form your paper. Okay, so you are reading paper not just for understanding everything what the authors have written, but it is for triggering some new ideas. So when you listen to talks also, you can daydream a bit, come up with some new idea. Okay, so that should be your goal. Only then you can be some kind of innovator, you can have new ideas for your paper.
So, what new materials do you think can be explored in this spintronics or magnetism later?
Okay, so there are many materials. So some people are interested in something, some people are not interested in something. So in my case, my group, we are looking at orbital torque. Okay, so so we learnt about using spin orbit torque to switch magnetization, right? So now we are still working on this one, but we are also looking at using orbital Hall effect to switch magnetization. So the beauty of this is that I mean theoretically it is claimed that orbital Hall effect is much larger in magnitude compared to spin orbit torque. So if you can convert orbital torque to spin, then you can use this spin to switch magnetization. So this is one area which I am working on, my team. Then the another area that we in our group we are working on is alter magnets. So these are new form of magnetic materials people have proposed. Yes.
What does it mean converting orbital Hall into spin? And how do we
Okay. So the problem is okay, if you call L the orbital moment does not interact with the magnetization or magnetic moment. Okay. So you need some intermediate thing, so that you can use this to switch magnetization. Okay. So this is a bad example, do not use. See, dark background I am using red color, you cannot see. Okay. So we want to switch magnetization using orbital magnetic moment is not possible. So what we do, we use the LS coupling. So you know that orbital moment and spin moment can be coupled, and we have learnt so far in many lectures that we can use spin to switch magnetization. Okay. So when we talk about something like this, to give you practical example, let us say chromium is a orbital material, let us say there is a orbital Hall effect in chromium. So this chromium will have some orbital torque, some kind of L will go up, some kind of L will go down, but this L cannot switch the ferromagnetic layer. So what we do, we use some materials like a thin layer of platinum. Okay. So platinum has heavy spin orbit coupling. So this is spin orbit coupling, right. So platinum can convert L to S. So because of this platinum, now spins are coming into ferromagnetic layer and they can switch magnetization. So that is what I meant by SM like that. So just depositing chromium on ferromagnetic layer, you cannot switch magnetization, but by using some metals like platinum, you can convert the orbital magnetic moment into spin magnetic moment and use this spin to switch magnetism. Okay. Anyway, thank you all. So, I enjoyed interacting with you all the time. So, thank you very much. Okay, done. Questions, I mean, they said it's all easy. So,
okay.
No point, yes.
They find it easy means they have learned.
Yeah, yeah.
Okay. Good afternoon, everyone. As we come to the last part of the last chapter of this wonderful sessions, where we have lot of learning, discussions, and lot of knowledge sharings. So now it's time to express our gratitude and appreciations for the active participants, and to bring this session to a formally on a closed session. So we are honored to have Professor Harshal bin Hamade sir, head of the Department of Electronics and Electrical Engineering. I would like to request sir to please come on the stage and express few words with the audience.
Distinguished guests and participants, I hope you have enjoyed the course. At the same time, you had enlightening experience learning in this emerging field. I'm sure, I don't know whether you know or not, Professor Prem has been diligently working on this topic and preparing notes and course material for you for this 10 days, day and night. Even Professor Datta had sleepless nights preparing the course material. So I thank them for dedicating devotion. Okay, so finally I would like to request you to provide the feedback. So in the feedback form, just don't tick. So we would expect you to write a few words, because you can express better when you write in words. Okay. So I thank Professor Prem for coming to IIT Guwahati, and I expect that we'll have more meetings, and you keep coming and updating us in this with the new new innovations and ideas in this field. Okay. Thank you, all of you. Bye.
Thank you, sir, for expressing your words. Now I would request Professor Prem sir to please come on stage and share his experience and some feedbacks for our participants along with this journey.
So good afternoon, Professor Namade. Good afternoon, Professor Datta, and all the students. So I had very fun full of 10 days. I enjoyed interacting with you. I hope you also enjoyed listening to the lectures. I hope it was fruitful and you have learned some new topics and gained new knowledge. So at this point of time, I'd like to thank Professor Datta for inviting me. So we know each other for close to 10 years now. And I also would like to thank all the volunteers like Atul, Subankar, and many other colleagues from Professor Datta's laboratory. And also I'd like to thank all of you for most of you are very keen in learning. So that's actually the most satisfying thing for a teacher. So if you all ask question and if you show passion to learn, that is the most fulfilling thing for a teacher. So I really felt with all of you. With that, I thank you all. Thank you very much.
Thank you, sir, for experiencing your words, and thank you for taking this course and sharing a lot of knowledge with us and our participants. And we would expecting more interactions with you in future. Now I would like to request some of the participants to come on the stage and can share their feedbacks or some experience, whatever they have gone through in these 10 days. So any one of you or two of you can come on the stage. So no one wants to express something. Can come, anyone can come and express their words if want. No, I think someone can come and.
I'll throw this arrow.
So the spin will decide. Okay, if not coming on stage, you can just share words by standing there only itself. Sipra in the last.
Would also come here and speak.
Yeah, I don't mind, but
please come.
Hi everyone, myself Shipra. I'm currently doing my PhD from Center for Nano, and my background is optoelectronics. So basically, I have no idea about magnetism and all. So it's been so long after my masters, I've forgotten all the concept and everything. So just to refresh my understanding, I joined this course, and it was so enriching. I learned a lot of things about magnetism and all, and also about the new discoveries and what work is going in terms of research. And I also feel I can somehow, I can also with other people, I can somehow relate and correlate my work. So it will be, I think, fruitful for my future. So yeah, thank you all. Thank you, sir. It was really nice. You were a really great teacher. Thank you.
Thank you, Sipra, for sharing your experience and the learning things you have done in these last 10 days. So I would like to request any other participants if they want to express something regarding our Prem sir or regarding this course, or the course coordinator Tanmay Datta sir. Anyone, if they can come on stage, or they can say from there only. We can pass you the mic if you are afraid of coming.
Come here.
No, mic. Only mic दे दो.
Mic.
So thank you, sir, for this 10 days. Actually, my work is not purely magnetism. So I work on ferroelectrics as well. So some of the concepts were not clear to me, and it would have taken me years to grasp the concepts. And through this course, I have learned a lot. And I think your knowledge in this area, it reflects from the very simple analogies that you can give. So I have gained a lot from this course, and I think it will be useful for my research as well, whatever I got from this course, be it from the lectures or from the tutorials. I think I can put to use. So this course has been very grateful, has been very helpful, and I'm grateful to have joined this course. And also I can also, next time if some such course is there, I can recommend for my peers also to join. Thank you.
Thank you, Nafisa, for your words. Okay, so any other participants? Are they interested to say something? Okay, if not, then.
Girls seems to be more sharing. Boys somehow are very discreet, huh? Spin polarized. There is a polarization already here. So, any of the boys would like to speak of something?
Okay, one of the.
Hi, myself Kulbhushan, and I works on fundamental aspects of magnetism. And for me, till now, the spintronics was like, for me, like spintronics was like some half metallic systems which I have studied, and the great like a larger value of resistance in some multi layers. I didn't know how these phenomena work in this in a device kind of systems, and I learned a lot here. And one thing which was really interesting is how sir presents these ideas in very simple terms. That was really nice, and I come up with new ideas in the field and want to explore more here. So thank you so much, sir.
Thank you, Kulbhushan, for your words. And so, any other participants? Okay, if not, then we'll. Okay, yeah, one more participant there.
Thank you, sir. Thank you, Prem sir, Tanmay Datta sir, for giving us the opportunity to learn about spintronics. My name is Rimli Sekia. I'm currently working in INUP projects in Center for Nanotechnology. So I took this opportunity to learn about spintronics. So before coming to the course, I searched the YouTube for some knowledge about spintronics, but I didn't find any good material on the topic, since it's a new topic, and the application part, I don't think it is quite available in YouTube and other materials. So I don't mind, but I have done the susceptibility and temperature plot wrong. All the two questions I had marked wrong in yesterday's exam also. So I have confusion in my basics, but I can say that I have learned from sir the application part. I have learned quite well. I have grasped it, but I'll try to relearn my basic once again. So thank you so much, sir.
So the YouTube recording is available. I mean, the recordings are available in YouTube, so you can always watch it.
Okay, thank you. Okay, any other participants? Okay, if not, then we'll proceed with the certificate distributions. So I would like to
someone also can say about the organization, right? So that the students and the CET team, maybe Pallav.
Yes, I'm Pallavi. I am here on a short-term project under INUP. Thing is, I have been interacting with this group almost close to 6 months now, and it's really a wonderful team, and I'm really feel very happy and lucky to be part of this group, even for this short duration. and I know how much effort they have put, at least glimpses of it. I'm not directly involved in arranging all these things, but from my perspective, they have put a lot of effort to organize all these things, and I say it's a great success in terms of organizing the events and making facility easy for people who have come from all over the country and all. So my heartfelt thanks and gratitude to Tanmay Datta sir and all my lab mates and friends, Atul, Shubhankar, Devdulal, Valyur and Shivender and Sriram, to everyone. Thanks a lot to you, sir. And one last thing about the course. I mean, two important things I would like to stress upon is the breadth and coverage of the topic, list of topics. That was very great. So many major topics covered in 10 days. Second aspect is the way those things were covered and explained. There are many competent researchers in the field, but very few are skilled in rendering a topic. Teaching is a different art and talent, and Prem sir is very skilled and very talented in teaching. So thanks a lot to Prem sir, and thanks a lot to Tanmay Datta sir for bringing him here and making this course possible. Thanks a lot.
Okay, so taking all these good feedbacks and supportive feedbacks from the participants, I would like to proceed with the certificate distribution ceremony, and I would like to invite Professor Harshal bin Amade sir to kindly come forward and distribute the certificates. So I will be calling the name of the participants, and they can come and they can receive the certificates. Astha Tiwari, Nilot Paldeka, BN Pallavi, Amlan Misra, Muhammad Ayan Anwar, Hodam Karanjit Singh, Sipra Aswal, Chaitanya Yadav, Subhajit Das, Suprabha Mandal, Kaustav Bhavne, Nafisa Bingson, Rimli Sekia, Sanskriti Chanda, Kulbhushan Misra, thank you, Nemade sir, for your valuable presence. Now I would request Professor Prem sir to further proceed with the certificate distribution of the participants. Ritik Roshan, Vigit KB, Athira P, Bodhisattva Dalai, Shivendra Pratap Singh, Priyanka Sharma, Naveen Kumar KR, and Guru Prasad Panda. Okay, left. Okay, we can. Okay, we'll do it later. Okay, we'll do it later. So before going to the final closing sessions of this tutorial or this course, I would like to give my personal feedback to Prem sir and Tanmay sir that my background is electronics and my master's is completely on the optoelectronics. So in my PhD, I have choose to work on the spintronics since I found this field like interesting. But when I started my PhD journey in 2022, I struggled a lot with the very basic terms also to find. Okay, neither I can find some in very simple way the way the professor Prem sir has taught us. I have never find anything in very simple terms in any books or in the YouTube videos. So me and my colleagues like Subhankar, those who have started PhD with me in the spintronics field, we have struggled a lot. So now we come to know the value of this course after the struggling of 2 to 3 years to find even the very basic things or the concept of spintronics that can be explained in a very simple way that were done by the Professor Prem sir. Thank you sir for this, and I would like to say one more word that we'll have a future interactions with you sir, and if you have me and any participants will have any doubt or anything to discuss with you, we'll approach you. Thank you so much, and I would like to thank Dr. Tanmay Datta sir also for organizing this course, and Professor Harshal bin Amade sir for to present here for this closing ceremony of this course. So thank you everyone, and to officially close these sessions, I would request Dr. Tanmay Datta sir to come on the stage for the closing remarks of this Gyan course that entitled as Spintronics Memory, Physics and Technology. Thank you.
You wanted to say something? No. Okay. Yeah. So good afternoon again. I was standing here, I think, how many, 10 days back? 9-10 days back, we were all here, right? So we began a journey, and today we kind of, let's say, I would not like to say end the journey, but let's say we kind of put a pause to this journey. I think our learning journey will still continue, but this is a phase of that learning process which you undertook here. And I really hope and I believe actually that all of you have learned a lot in the last 10 days, and I am pretty sure that you when you return to your individual institutions, you would be returning with way more knowledge and experience about the basics of this field as well as the technology in this domain, right? So I have not been able to follow all the lectures, but I have been trying to follow online and offline his lectures through YouTube or sometimes here, and I have seen some of the instances how he has put across the concepts, right? So for example, I think one day I saw that he was teaching this STT spin transfer torque, right? And right before that he was teaching spin polarization, right? So generally spin polarization would be covered by someone as like a very basic thing way before they reach to something like STT, but he put these two concepts together, and I asked him actually that day that you put spin polarization and then next to it you put STT, and then when he said that, I just wanted to carry forward from spin polarization to STT because it makes more sense, right? And I also thought about it, actually it is, right? So it's not about the content. I mean, as you said, there are micro contents available, there are contents available. I mean, not so much, but they're still there. But the way a teacher organizes it and then delivers it, I think is very critical. So this is one instance how he thought to deliver in his own way, and I think it's true that that helps if you follow this topic, spin polarization with STT, right? Similarly, I think one day he got this what is it called? Fidget, right? So he got that fidget. Again, I asked him, what are you going to do with that fidget? So what did he do with that fidget? Angular momentum, right? Spin and angular momentum. So he brings he delivers these things in his own way, and I have always seen him. I mean, as he said, we have known each other for like 10 years since I began my PhD, and I have always found him to be very good at this of explaining concepts, very difficult concepts. And spintronics, of course, is not a very easy the concepts are not very easy, and there are very few who can actually deliver it with such ease. So I really admire that capability. I told the same thing, I think, in the beginning, and I think now all of you would be able to relate to what I said on the inaugural day, right? So thank you again, Professor Prem, for agreeing to come here. It has been very hectic for you, I know that. I know how our dates have changed, shifted, schedules have changed, and so many things. Like, I think last if I am not wrong, we have been discussing the dates since last November, correct? Since last November, we have been trying to freeze on the dates again and again, and then so many things have come up. But nevertheless, he has made exactly 10 days to come here and deliver it. The ideal situation would have been him coming here for 14 days, rather 13-14 days. But again, he had something to attend just before he flew here, and he has something to attend again on Monday morning in Singapore. So it's very nice of him to really make time for us and deliver this. I'm really thankful for that. I am very thankful to all the participants here. I think the online people are not here with us today, right? They are not joining. Okay, but I would like to thank the online participants as well as offline participants here. You have been very actively participating. I know that the first day, the 2-3 UCLAP slides did not have 100% response, but I think from then on, from the first 2-3 questions, we have been seeing 100% and instantaneous response. All of you got familiar with that, and you very actively participated, right? Also, I think your interactions, yesterday we had the poster session, so I heard, there was interaction with all of you, with me, as well as Prem sir also interacted with you, and we could see, there's a vast change in the way you are already dealing with the concepts. Some of you expressed concerns that how do we present a poster, because we don't work in this area, right? And some of you presented with very basic things that you have learned in this area, and that's also amazing, wonderful, right? I hope you all had a great stay here. You will all cherish these moments in your career going ahead, and I also hope that all of you will be able to pursue careers in this domain, be it at the master's, PhD or postdoc levels, and you will all benefit from this in the long run. Okay, so I would ask everyone to join me in applauding your efforts for the last 10 days. Okay, so a loud applause to all of you. So I would also like to thank Professor Nemade here and our Dean Administration, who is not here today. He could not join us, unfortunately. And the entire administration at IIT Guwahati, the CET team, they have been working in shifts, and they have been really being on the top of their work, relentlessly trying to make everything work smoothly without any hiccups, right? Specifically, I would like to mention that I have seen many online lectures being recorded, and I was following these lectures on YouTube. So I don't know if you have seen it. If you have not, just go back and see. You will see that the team from the control room is so adept at this, that every time he is speaking, they will pan out, and he's showing something, they will pan out, and you will have an entire view. And when needed, they are actually panning only on the screen, right? Only on the screen, the screen is shared, and again there are when there is student interactions, there is this camera is being switched on, right? So all the multiple cameras and the screen share, everything is synchronized with the way he is delivering the lecture. So that's like hats off to the CET team. They have been doing a marvelous job at exactly, it's like a IPL broadcast. We just don't have that robot dog here, but it's like a IPL broadcast. Amazing. I mean, good job, I mean, by the CET team. So thank you to the entire CET team, right? And finally, coming to the TAs, volunteers, they have had, I think someone said I have had sleepless nights. I actually did not have sleepless nights. I think Professor Nemade said I still had some sleep. I would say the team organizing this, the TAs actually had sleepless nights, right? None of us would have organized this without their relentless work prior to this, and also during the duration of this program, right? So at 12 a.m. also we are receiving emails from them. Professor Prem and me are receiving emails from them at 12 a.m. about different things, right? So they are working they have been working day in, day out, and they have managed all of this in spite of their own research that they are continuing. So none of them have stopped their research, right? I mean, they are all PhD students. They have not stopped their research. They're continuing their research. On the side, they are also helping with this course, and they have not only helped, they have actually pull this entire course through on their shoulders, right? So a round of applause for all of you. Really great job, right? Thank you to all of you. You have done a great job, right? So so with this, I think I would like to thank everyone who has been a part of this program, and look forward to seeing you, meeting you, interacting with you in different roles somewhere, right? And Professor Prem will probably be visiting us, not probably, definitely visiting us in another few months, right? And let's see, we are also thinking of organizing a symposium then. If we can, we'll again extend the invite to all of you to come join in the symposium, right? So with this, I would like to conclude this session. Yeah, thank you so much. We will have lunch served after this, but probably with a delay of another 5-10 minutes. Please bear with us. I know you're hungry. Right, your hunger for knowledge is, I think, partially quenched, but the hunger for food, I think, still remains. So join us for lunch and have a safe trip back home for those who are going back, and all the best for your careers ahead. Thank you so much.
Thank you, Tanmay sir, for your words and sharing your thoughts. So before going for lunch, I would request for a group photo for all the participants. So please come on the stage and we can take a group photo together. Thank you. Yeah, and yeah, bring your certificates.
So sir wanted a photo like this, huh? Better than a photo like this.